All right, let us look at some examples. I want to do a sample problem for a network that is directed, meaning each of the edges connecting some of these nodes have a direction to them. And then afterwards, I want to do something very similar, but in the undirected version, where I can travel back and forth on all these edges as I want to. So the first one gives you the network here, and I want to find the shortest route from node 1 to node 7. Okay, so in my Excel file that will slowly build, formulate the problem, then implement it using Solver. I have the picture over here, so the flipping back and forth is not so bad. So my model will look like a linear programming model, integer programming in this case, or a binary model, but it has the same three parts to it. Formulate uh, by way of defining the variables, the objective function is next, and then the constraints. Now, often with the um, integer programming and the binary models, I do sort of think of the variables and the objective function at the same time. But in this case, what are we looking to do? Well, we need to decide, well, let me ask this. What decisions do I have to make? I need to decide, am I using this edge, this connector, this line from node 1 to node 2 in my route, in my journey from 1 to 7? I have to decide. I'm going to use this one. I want a bigger mouse cursor. Why can I not get a bigger mouse cursor? I want one. Give me something bigger, please. There we go. Oh, that's way better. Look at that. Beautiful. This line here, I decide. Should that be in or not? I don't know yet, right? But it's a decision I have to make. This line here, this one goes towards 1. So probably not, but it's a decision I have to make. Should I travel along this line? Yes or no? Should I travel along this line? Yes or no? Yes or no? Yes or no? Yes or no? So I have all these decisions to make in order to establish a route from node 1 to node 7. The lines are the decisions. Include them, don't include them. So that tells me what my variables should be. So I like to ask myself, what is the decision I have to make here? So I'll say let x, for example, I'm just going to do one example. I'll say x12 be 1 if, let's just say line, uh, let's just write it out. The line from node 1 to node 2 should be included. And I'm going to write it on the second line. Let x12 be 0 if the line from node 1 to node 2 should not be included in my route, right? So those are decisions I want to make. So for a binary variable, I like to say, what does 1 mean? What does 0 mean? So it's a little bit more wordy, but it's easier for me to follow. Now, of course, that was just one edge. I have to do it for all of these, all of these. So I need to make this a little bit more general. So I'll say here from node I to node J. And then this one as well, right? From node I to node J. Now, it might be helpful to use the diagram because I don't have a variable for any I value and any j. For example, um, 1 goes to 2, so there's a variable x1, 2, but there's not a variable 2, 1 because I can't go from node 2 to node 1. So I do have to add a little bit uh, to that. So I could say here, um, this could be for I, oh, not a capital. Excel always capitalizes because they think it's a sentence like me as in I. For I and j, um, such that node I, I to node j has a line in the network. So you could say something like that, right? So I'm not going to have x14 because I can't travel from 1 to 4. I will have an x41. So these I and j general options that I have can't just be anything. Only those that make sense in the network according to the lines that I have. Okay. An option also is I could make and refer to what we call an adjacency matrix. Just an option, it's not necessary, but I find it helpful, especially when things get a little complicated or bigger. So I want to keep track of my nodes, and I'll have 1, 2, 3, 4, 5, 6, 7, potentially being attached to the same nodes, right? Like so. Maybe we want to bold that, make it stand out a little bit. I don't know. It's up to you. Maybe like that. And then I'm going to put the weight here, 65, which could be the distance that I have to travel. It could be a time. It could be anything, right? It depends on the actual practical problem. That's not the issue here. The issue is how do I handle the essence of this kind of problem? In this case, I'll put the edge weights, the line weights over here. From node 1 to node 2, I travel with a weight of 65. The arrow is working with that. But from node 2 to node 1, there will be nothing because I can't travel that way. So from 1 to 2 and 1 to 3, I have some options. And that's the only options I have from node 1. From node 2, I can travel to 4 with a weight of 32. Now I know I could have done this beforehand, but I want to do it from scratch so you don't miss anything. From node 3, I can travel to 4 with a weight of 37. And that is it. Everything else goes into 3, right? From node 4, I can travel to node 1. It's an option, probably not the best, but that's for Solver to decide. I'm not going to rule out anything. I can also travel to 5 with a weight of 56. I can travel to 7 with a weight of 28. So this adjacency matrix is really just uh, duplicating the information in the diagram. It's optional. Some people like it. Some people don't like it. The diagram, the adjacency matrix, they are the same. So I'm just giving you options. From node 5, I can travel to 7. That's about it. The others are all coming into 5, this one and this one. From node 6, I can travel to 3 with a weight of 78. I can travel to 4 with a weight of 31, and that is it. And from node 7, I can travel to node 6 with a weight of 47. So you can also define your variables according to entries in the adjacency matrix. Because the network and the adjacency matrix, they are the same, they have the same information, I can reference either one of them. So maybe we'll do that when we set up the objective function. Again, just giving you options, but it's all the same thing in the end. So objective function, we wish to minimize the, let's say, total root weight R, where R is going to be the sum of the variables. Now I have a lot of variables here, not too many, it's manageable, but I can quickly see that if this network gets even a little bigger, I'm going to have a lot of stuff here. Essentially, for every weight entry I have in the adjacency matrix, I have a line in my network, right? An edge. So how many variables do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's not bad. It's not terrible. And I can certainly go and say, okay, x1, 2 plus x1, 3 plus, and so on. However, remember what the decision variable is. The decision variable on its own is just 0 or 1. Is it included? Is it not included? The weight isn't factored in here, but it should be. So if the edge 1, 2 is selected to be in my root from 1 to 7, then it's going to contribute a weight of 65. If it's a 1, it'll contribute 65 to this total root weight R. If it is a 0, that means that is not an edge I'm traveling on. It'll just cancel that whole thing because the variable value will be a 0. So I put the root weights, sorry, the edge weights in front. So I totally can do the next one here, which is 32 times x to 4. Now in this case, I'm going to do the whole thing so that you can compare different ways of formulating the objective function. They're the same. So please don't get confused. This is not a 12. This is my naming system for the variable. And if you want, put a little multiplication there in front. Maybe that confuses people. Let's do that. And then we will have, let's just do them all, right? Doing one example from start to finish, all the detail. And you can scroll back and forth as you need to. 2, 4. And then I have x to 5. And then I have, make sure you don't miss one, 3, 4, which has a weight of 37, x3, 4. And then I have this guy, unlikely as he might be in there. x4, 1, probably not though, but that's for solver to decide. 56, 4, 5 to 4, so, sorry, 4 to 5, x4, 5. And then I have here 28, 4x, 4, 7. And this isn't even a big network, right? It gets quite tedious to do them all like this, though it is perfectly correct. Then I have 3 more, 78. Ooh, that's a heavy one. A weighty one. But solver will decide what is best. I am not going to assume that I can do the job of solver. Sorry, what's this? The weight is 31. And then it is 6, 4. Last one, which will have a weight of 47, space there, 47. And it is x76. Okay, perfectly fine. Let's just say here, an alternative way to state the objective function. Nothing wrong with that. But I can see that if this gets lengthy, then surely this is not going to work in a very efficient way, right? So I could say where R is the weight for corresponding to variable ij times xij, but I have to add them all together. So I'll say the sum of this calculation, because that's what it looked like every time, right? But I can't just say that. I have to say uh, with wi, not with, maybe for wij having a positive entry in the above adjacency matrix. You could say that. Perfectly fine. And then you need your adjacency matrix in combination with this formulation. People can say, oh, I could write it out if I want to. This is it. But you don't have to write it out if you have all the numbers here, right? It's just a matter of how can I efficiently and still correctly state my objective. Okay, now you choose. You choose. I don't know your experience level. It's whatever you are comfortable with. You can write out your variables one by one. You can be more efficient in your formulation, but we still want to be correct. So there are options. You can just look at the diagram. You can use an adjacency matrix. Options, options. So now what are my constraints here, right? Well, the constraints are essentially explaining in a different way what what goes in and what goes out along this network. That I can't travel from 1 in just any way. I can't travel towards 4 in just any way. If I look at node 1, there's a certain structure around that I have to obey, and so on. So for every node, there will be a constraint. Sometimes I like to write here subject to the following constraints. Have words there. Say what you're doing. It's good. Node 1. Every node will have, oh, it doesn't want me to, it's fine, I'll just copy them. Every node will bring its constraint. And I highlight which one I'm looking at when, so that I don't get confused. I don't do them all at once, but when I look at a node, I have to see what does the network tell me for that node. I have one too many here, that's no problem. So I'm just going to pull this guy down so that we can see things at the same time. Beautiful. Okay. So let's just do all the interior nodes, not the starting node, not the end node, because all the interior ones will have a similar look to them. Now, again, we have so many options. Everything has an option, it feels like. But it's not a bad thing. But once you have a way that you're comfortable with for doing these things, don't mix and match, mix it up too much. Try and be consistent from one problem to the next. So your options here are, are to uh, write it out in maybe a more logical way and then simplify the inequality to make it ready for solver. That's fine. Let's do node 2 like that. So essentially, what comes in must go out because node 2 is an internal node. It's not the start, it's not the end. So what comes in to the node, let's say in has to equal out. What does that mean? Well, I start with the concept and then I'll flesh it out using my variables. Now the diagram is perfectly fine, but of course the adjacency matrix would do the same thing. So If I want to now elaborate on what's going in here into node 2, well, x12 is going in and nothing else. So if I'm going into node 2, x12 will have a 1 because I've used that edge. But if I go out, x24 or x25 should also have a 1. They can't both have a 1 because then they won't balance. So the amount of times I'm coming in should be the same as the amount of times I'm going out. Now, we have made a little assumption here for simplicity, but there's no rule that tells me that I can only travel on an edge exactly once. So technically, we can make this a little bit more general and say uh, the variables, the decisions can be don't use the edge, use it once, use it twice, use it 3 times. Maybe I want to travel over the same edge multiple times. In a larger network, I don't necessarily want to exclude that option, but I already have extra knowledge that says that'll never happen in a shortest route problem. I'll never double up an edge, but in general, we could have maybe might not have had that knowledge, and we could have expanded this to say um, let xij represent, say here, uh, like this, represent the number of times the line from node 1 to node 2 should be, let's say, used. That is a little bit more general. And then solver can decide, should I only use this edge once? Maybe I want to do something, travel and travel back through this on my way to 7. It is a little bit more general, and solver will then decide, and if I use it twice, xij will be 2, and I'll add the weight twice here in my objective function. So it's perfectly valid to be a little bit more general when I don't maybe know that looping back onto the same edge is never optimal. So again, options, so many options. So then it becomes an integer problem and not a binary problem anymore, but solver will figure that out. So we can leave that. Regardless, my issue here is still the same. My issue is regardless of how many times I come in, x12 counts that. The number of times I'm coming into the node 2 has to be the same as the total number of times I'm leaving the node 2. Right? So maybe in some more complicated situation, I come into node 2 twice. Once I exit to node 4, then x12 will tick 1, x24 will tick 1. And another time, maybe I'll come into node 2 again and exit towards node 5. Then x12 will tick another one to total 2 uses of that edge, but the other 2 will only use 1. But the total number of times in has to still equal the total number of times out. Okay, that's what that constraint says. Now I can simplify that because I know solver is coming up. Solver wants every variable on the left. So I could just move everything to the left according to, oops, no, it's not a plus, it's a minus. According to my rules for simplifying equations, like so. Because it's quite straightforward, in this situation, the edges in to the node will have a positive. The edges out of the node will have a negative. You could jump straight to this one. You don't need to set up the maybe more logical one first and then the simplified one. It's completely up to you. Again, the theme of this is know your options. So let's do node 3 in the automatically simplified way. I'm going over here. I'm coming into node 3, so x5, 2. Sorry, no, not, that's the weight. x1, 3, right? So easy to stop thinking for a second. And I can also come in via node 6, 6, 3. If you remember here, 6 to 3 has a weight as well. But then I have to leave by going to node 4, so that gets the subtraction equals 0. Again, maybe let's switch up the next one. Let's switch up the next one to be maybe the basic logical one first, and then you simplify. Options, options, options. Node 4. How many ways can I come into node 4? Maybe from 2, and then I can come in from 3. I can also come in from 6. It's easy to miss some of these. In, in, in. Those are all out. Okay. The number of times in must equal the number of times out. Out towards 1, out towards 5, out towards 7. So I have a total of 6 edges. 1, 2, 3 in, 1, 2, 3 out. So that looks good. I'm just going to move this over 1 so I have some space. And then my simplification will be, I'm just going to save myself a little bit of time, copy it over, and just edit this to be minus, 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 and then equal to 0. Know your options. Choose what's comfortable for you. Let's do the last two internal nodes. Node 5. I have coming into it from 2, also from 4, and out to 7. Node 6. I come into it from 7, and I go out to 4 and to 3. All right, now the first one, node number 1. Node number 1 is different because that's my starting node. So the number of times I come into the node versus the number of times I go out is not the same. It's not the same. The number of times I come into the node will be from 4. How does that compare? I don't know yet, right? I'm thinking about it still, trying to understand the reasoning and how that constraint inequality equality reflects the concept. So I'm coming in versus going out to 2 or to 3. So in order to ensure and essentially tell the model or convey the information in the model that this is a starting node, the number of times coming in is not the same as the number of times going out. If I rewrite it to the simplified version, the number of times coming in, not 1, 4, that's not right. What am I doing here? I have to engage my brain. That's kind of important. Coming into 1 from 4, so 4, 1. Take away the number of times going out, which is x1, 2 minus x1, 3, because I could also go out there. What should that equal? Well, if this is my starting node, then I'm going to leave it first maybe never come back. So the number of times I'm leaving it should be one more than the number of times I'm coming in. Let's suppose I start at 1, I travel out, tick 1 for leaving, I maybe come back to it, I enter it, that's 1 for coming in, but on my way to 7 I have to leave it again. So I would have left it twice, came in only once. The number of times I leave it has to be one more than the number of times I'm coming into it. So you could do this in two ways. I could say the number of times coming into it, I have to add 1 to match the number of times I'm leaving it. Or you could say if the number of times I'm leaving it is 1 more than the number of times I'm coming in, to balance this equation, I have to subtract 1. It's the same thing. So the starting node is a little bit different. A little bit different. Same for the ending node, which is node 7. I have to tell the model that this is the ending node. I can't just travel in and out through it. No, it's the same as the starting node, just a little backwards. So if I come into it with 5 to 7, and I come into it from 4 to 7, how does that compare versus? How does that compare to my exit option 7 to 6? Right. Well, in the finishing node, let's suppose I only visit node 7 once. The entry will be 1 tick, and I never leave it. So the number of times I enter the node is going to be 1 more than the number of times I leave it. Let's suppose, for some absurd reason, I can't even imagine, I enter it, but I leave it as well. I still have to come back to 7. So yes, if I enter it and leave it, that's 1 each. I still have to loop back and come into it. So I would enter it twice eventually, but only leave it once. So the number of times I enter it is 1 more than the number of times I exit it. So now you can say if the, in this case, left-hand side is 1 more than the right-hand side, I have to add 1 to the right-hand side to balance the equation. And that then, when simplified, x57, I could have copied that, I know. x47 minus x76 equals 1. So the simplified versions are always number of times into the node minus number of times out of the node. Number of times in, take away the number of times out, has to be 1. So that I stop there. I travel into it 1 more than out of it. Whereas it's the opposite for node 1. I travel into it 1 less time than out of it. It's the -1. Whereas for the internal nodes, I travel into it the same number of times I travel out of it. And there we go. Now we're not completely done. We have our, it depends which way you want to look at this. Technically, to be as general as possible, we have our integer constraint here. Let's say here, integer constraint. The xij's are integers, well, positive integers. Positive in, no, non-negative integers. It's not the non-negativity constraint, it's more than that. For, we could say row I, and, oh, not a capital I, and column J having a positive entry in, ooh, I'm running out of space, in the adjacency matrix. So I can refer to the adjacency matrix to help myself for any one of these. 1, 2 as a variable, x1, 2 should be a non-negative integer. Again, I'll accept it if you have this as a binary model. It's all good. It's all good. But it's interesting. Let's see what solver does. Let's see what solver does. So now I'm ready for some solver action. Let's write. Here I don't have a choice. I'm going to have to write all my variables. But I already. Oh no, I don't have it. I'm going to have to write it out. It's a little annoying, but I really have no way around it to set it up for solver. x1, 2, x1, 3, x. You can. Oh, let's just hide this, right? Let's hide this temporarily because I need to see my adjacency matrix. That'll make things much easier. x1, 2, x1, 3. Next one is x2, 4. Yeah, that's way easier. x2, 4, x2, 5. No, not in the same line. I pressed the arrow. The arrow did not respond. I'm over here. x3, 4. I need to move my diagram up. x3, 4. I'm over here. x4, 1. Then I'm over here. x4, 5. Then x4, 7. That was that one. Then x5, 7. Then x6, 3. x6, 4. That was that one. And x7, 6. I could count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, beautiful. Beautiful. Now, you can have your layout slightly different ways here. I'll put the values maybe at the top if I can learn how to type. And maybe I want to color them yellow. Sure. And then maybe my objective function R, I'll put over there. Oh no, I usually put it a little lower. Let's do it over here. I'll make that maybe green. Your color coding might be different. Doesn't matter, right? Here is my objective function coefficients. Well, it comes from the adjacency matrix. Let's put it in. 65, 52, 32, oopsie, 76, 37, 91, 56, 28, 38, 78, 31, 47. Beautiful. I like to put some numbers there just so I can check my formula, because my formula is going to be the sum product of these guys with these guys. Close my bracket. It's up there if you want to see it. It's not that, oh, 631, obviously, but having numbers in here helps me to just check the sum product function is doing what I want it to do. Then my constraints will be something that is hidden. Let's unhide this and have my constraints listed over here. I need to see both, which I can do luckily. Now, my constraints are all equalities. So over here, I'm just going to zoom out a touch. Just a little so I could see them all. Over here will be the left-hand side values of my constraints. I like a nice blue there. They will all be equal constraints. Their right-hand sides will be -1, then a bunch of zeros, and then a 1. Okay, that sounds good. Now I look at the coefficients in the simplified versions, put them in. So x4, 1, x1, 2 gets a negative, x1, 3 gets a negative. That is it. Node number 2, x1, 2 gets a positive, x2, 4 gets a negative, 2, 5 gets a negative. I read it off my inequalities. I don't rethink the model here. This is now the implementation. Big difference. But many people don't do that. Many people formulate the model in here. No, no, that's not at all what I want to do. x1, 3 for node 3 gets a positive. x6, 3 is way over there. x3, 4 gets a negative. Node 4 is a big one. 2, 4, 3, 4, 6, 4, and then 4, 1 is negative. 4, 5 is negative. 4, 7 is negative. Node 5, 2, 5 is a 1. 4, 5 is a 1. 5, 7 is a negative 1. Where do these ones and negative ones come from? It's the coefficients of the variables, just in case. I realize I did not mention that. But at this stage, that should be straightforward, I would hope. 6, 4 gets a negative. I'm just trying to not make a mistake here, right? A mistake here and everything goes very, very badly. 5, 7 gets a 1. 4, 7 gets a 1. 7, 6 gets a negative 1. Beautiful. I like it. I like it. Then I want to put in my sum product. Top guys, which is my variable values I want to fix. And then the coefficients, close the bracket, enter. That'll get copied down. Double check a random row. See the top stays fixed. It's beautiful. I like it. Okay, we're ready for some solver. And of course, if this goes too slow, scroll ahead. If this goes too fast, scroll back. It's all good. That's the beauty of it. I want to solve some stuff. Solver's a little in my way here, but I want to have that as my objective function value. I want to minimize. Yes, I do. By changing these yellow guys, adding some constraints. They're all the same. They're all equal. Beautiful. Right-hand side, I love it. There's one more to add. All these variable values. I'm sticking to the general one, so those are integers. Okay, I have 2 of those. I do have to make the unconstrained variables non-negative, because I guess I could have negative integers as well. Check simplex, and I think we're good to go. Include the answer report if you feel like it, or if the question wants you to. Not really too interested in that, because my answer is over here. Now I have to interpret that. I'm just going to bring my diagram down, so I could see, does the solver answer make sense? What it says is 1 goes to 3, 1 goes to 3, then 3 goes to 4, and then 4 goes to 7. And that is the lowest weight, shortest path from 1 to 7. Beautiful. Now this is a fairly simple network, so I could have probably eyeballed it and tried some paths. I'm quite restricted here with the arrows and found, yeah, it has to be that one. But in a larger network, right, I can't do that. So the shortest route from node 1 to node 7 has total weight 117, and it is node 1 I'll do it like this to node 3 because x13 says exactly that. Then I have to piece them together, node 3 to node 4, and then to node 7 finally. Beautiful, beautiful. So there is a lot happening here, a lot, and a lot of options for how you can formulate this adjacency matrix. Not. You see here how I didn't need to make this a binary model. I could have, with extra knowledge, the shortest path is, sorry, the shortest route is not going to loop back because that wouldn't be optimal. If I loop back, if I go 1 to 3 to 4, and then make a little loop around somewhere else, back to 4, I could have removed that loop and found a lower total weight. It's never optimal. However, uh, Solver figured that out for me. I just say, I'll just visit every node a certain number of times, start node, finish node. You decide, Solver. Solver says, no, just visit them once and visit these. Otherwise, I won't have the lowest possible. So this can be set up as a binary model in this simple situation. I'll accept that. Technically, it's an integer model. And Solver then determines, oh, it's a binary solution, which when you think about it makes sense. Whereas if I try and build this out to handle fancier questions regarding networks, it's not always that simple. So I don't want to ever bring in my own assumptions. Otherwise, Solver isn't necessary, right? If I make my own assumptions, then what's the point of Solver? I need Solver to figure out what is the best. Take the model as it is. Lots of things to think about. It is up to you now. But this shows something from start to finish. Uh, Next, we want to take that same thing, but say, how, how is it different? How is it the same if we do not have any direction on our edges? What do we do then? I'll just stop the video here just in case I run out of time, and then we'll pick it up again.